All right, lesson 2. So lesson 2 is just a refresher, hopefully a refresher for you in angles, polygons, triangles, and quadrilaterals. So we got a lot of definitions, a lot of things that we just want to make sure that you remember. When we say something intersects, that just means they cross one another, right? Here we've got a couple of lines that are intersecting one another. Lines, we generally put arrows on the end just to signify that they keep going, right? They don't stop there. What would we say is the difference between this and that? What's the top one? Huh? Yes. The top one's a line segment because we don't have the arrows indicating that it goes on and on. And then this is a line here because it continues. A line by definition continues on in each direction, right? So these are intersecting lines. If I put arrows on the top and on the top one on the left and the right, now we have what kind of lines? Parallel lines, right? They're parallel because if I extended this out and kept going, would they ever cross? Parallel lines will never cross, right? Well, you can answer a lot, so let's go ahead and get you on there before I forget about it. Parallel lines will not cross. That's how we define parallel lines. What if they cross, and where they cross, there's a 90-degree angle?
They're just all right angles.
They are all right angles, so all the way around here it's right angle, but we have a special name for these lines. Does anybody know what that is? Somebody else besides Will? Just to give someone else an opportunity. So these are parallel lines, and usually when we talk about parallel, we also talk about no, huh?
Horizontal.
No. Perpendicular. Have you guys heard that term before? Perpendicular lines. So perpendicular lines are lines that cross and form 90-degree angles, right? At every angle that's formed by these lines. We could draw this little square all the way around there because to signify that it's 90 degrees on every side. All right, so those lines are considered to be perpendicular. What's another name for a 90-degree angle? Say it again. Yeah, 90-degree or right angle, right? That's my little shorthand for right angle. If you see that, that's what I mean by that. We do have something called a straight angle. And so if you just have a line like this, the angle that goes from this way all the way over to the other side of this line, y'all know how many degrees that would be? 180, right? 180 degrees, and so that is what we define as a straight angle. You could have, like the book has other lines intersecting that they have a line coming down here and forming a 90-degree angle, but the point is this whole thing is a straight angle, a total of 180 degrees. And then if we have an angle that is we have an angle here that's less than 90 degrees, and then we have an angle here that's greater than 90 degrees. Again, somebody else, give someone else an opportunity. What do you got? What do you got for less than?
Acute.
Acute is so cute. That's a cute angle. That's right. Excellent. Somebody else, tell me what kind this is. Hannah? Obtuse, right? So that's an obtuse angle. I don't know. The word obtuse kind of makes me think of fat. It's a fat angle, you know. Why would obtuse make me think fat? I don't know. Why? Obese. Yeah, that's why. It's like it reminds me of something that seems large. Yeah. So obese. It's an obese angle. So obtuse. Good. How many? What are the total of all the angles in a circle? So if I have a circle, and I had, we're going to draw down to a center point here, and just draw various angles in there. So there's a bunch of different angles formed by that. 1, 2, 3, 4 angles formed all together. But if I added all those angles up, what would they equal? 360, right? So all angles in circle add to 360 degrees. I'm trying my best And I'm just drawing a blank on remembering Cooper. Sorry, Cooper. All right. Good, excellent. So those are our definitions with lines and our definitions that we want to just remember right now as far as angles go. Somebody that hasn't said anything yet, tell me about a polygon. What is a polygon? Anybody want to take a stab at that? Is this a polygon?
No.
No. Why not? Because it doesn't connect, right? So that's one thing that we have to remember with a polygon. Polygons have to connect with one another. Says Liliana. Getting it? Getting there? So that's one thing that we have to have with a polygon. So what if I do this? The polygon now? Yeah, all right. As long as you've got these lines that connect, it's a polygon. Well, that. Is that a polygon? No. So that tells us something else about a polygon. What else has to be the
It needs
case?
to have angles.
It has to have angles. It has to have straight. It has to be lines, right? Technically, and then we all say straight line, right? Technically, a line is always straight. So it's sort of redundant to say a straight line. A line, by definition, is always straight. So it has to be comprised of lines, and it has to be comprised of lines that actually connect with one another. Now, and even lines, really, I guess technically lines are not the right choice, because lines just keep going, right? Like that. And so would that be a polygon? It's not, because the lines you can't have something like this where the lines cross one another. So really it's comprised of line segments, if we're going to be technical about it. Line segments that don't actually intersect, right? So it wouldn't be a polygon if they intersect. It wouldn't be a polygon if they aren't closed. It wouldn't be a polygon if it's got curved sections on it, all right? But anything else, as long as it kind of meets those different definitions, they would be considered polygons. So all of these, how many sides does a polygon have to have? It's going to have a minimum of what?
4
Nope.
or 3.
3. It has a minimum of 3 sides. Is it Cohen?
Mm-hmm.
It's spelled with a K though, right? Yeah. It has to have a minimum of 3 sides. Why can't it have 2 sides?
Because it wouldn't be a shape.
You're not actually able to connect the lines, right? If you only have 2 sides, no matter how hard I try, I can't connect it to that side without like curving around, right? So I'm going to have a minimum of 3 lines in order to actually connect it. But anything that has at least 3 line segments and that connects, right, is going to be polygon. So I've drawn some up here that are 3 sides, 3, 4, 5, 6. Do you guys know the names of these guys?
Triangle.
Triangle, that one's super easy, right? What about this one, based on the number of sides? Quadrilateral.
But like,
Huh?
I couldn't spit it out like.
Okay. Yeah, so quadrilateral. What about the 5-sided one? Pentagon, right? Our Pentagon building, right, in Washington, D.C. Well, actually, it's probably, I don't know if it's in D.C. It may just be in Virginia. 5-sided, right? How about the 6-sided one? I heard it very diminutively at the back. Who said that? Hexagon. There we go. All right. Hexagon. All right, excellent. So we could keep going, right? There's actually a list there on page number 5 that tells you a 7-sided figure is a heptagon, an 8-sided one is an octagon. You could think of an octopus, right? 8 legs, octagon. Nonagon is a 9-sided decagon. Think of a decade as 10 years, so a decagon is 10-sided. Undecagon, that one's kind of weird, is an 11-sided one, and a dodecagon is a 12-sided one. And then we can always, if we just want to say we're talking about some polygon and we don't maybe know the number of sides, we'll just say an n-gon. So it's n number of sides. So the n is just a variable that could represent any number of sides. All right? So what I want you to make sure that you know, the 11 one's pretty weird. I don't see that one very often, but I would like you to be familiar with 3 through 12. All right, so no names 3 through 12 minus 11 sided. That one's just a little less common. The 12 one's kind of uncommon as well, but I think it sounds cool. Dodecagon, you know? It ought to be some kind of cool dinosaur or something. I don't know, it's just a neat sounding name. So I want you to know 3 through 12, but you don't have to worry about 11. Another way that we can kind of describe polygons is we can use the term concave and convex, all right? So we might have one that looks like this, and we might have one that looks like this. Which one of those is concave and which one of those is convex? Somebody whose name is not on the board. Want to take a stab at that? Madeline? Concave is on the right. Here's the good thing, even if Madeline got it wrong, I would have still put her name on the board because she was brave enough to raise her hand and say, I'm going to try it, right? But she's actually right. And the easy way to think about it is which one of the figures looks like a side caves in, right? That's the easy way to remember. Now technically what it means is that can I put a point anywhere in here, and if I draw a line to another point in the figure, will it go outside of my polygon? And if I can do that, then we would technically say that it's concave, okay? There's nowhere that I can do that here. No matter where I put 2 points, I can't draw 2 points that's going to cross the boundary, right, of the polygon. So this one would be concave, it caves in, and then this one would be convex. All right, so make sure you know that definition. Any questions so far about polygons? I'm throwing a lot at you, and like I said, we're just defining some stuff, making sure. I think you've probably seen this before, but I want to make sure that you remember it. No questions so far? All right. Here's one. What if we had this here? And I want to ask, let's see, is anybody's name not on the board yet? Okay, so you are Allison, right? So Allison, do you know what these little marks mean that I've written along the polygon here? You have no idea? All right. What if I were to tell you that those marks meant that all of the sides, every side with that mark on it is the same length? They have equal lengths, okay? So this means all the length of the sides are the same. Do you know what you would call a polygon that's got all the length of the sides are the same? You can look at your book. Equal what? So you said equal angular. You chose the middle figure, right? But that has to do with the angles. This has to do with the length of the sides. So which figure only shows that the sides are equal? The regular polygon does have that. Look all the way to the left. Equilateral is how you say that. Yeah, equilateral. All right. So you took a good took a stab at it, Allison. I can see here. I am gonna have to be though. Everybody's on the board now, so I'm gonna have to be a little more selective on writing your name on the future. Writing your name on the board in the future, so that we'll make it a little more challenging to get your name on the board. But we're just getting started. So again, I want to encourage you guys to talk back to me. So this is an equilateral. Okay. If all of the sides are equal to one another in length, then we say it's equilateral. Now, if you have a polygon in which all the angles are the same. And the way we would designate that is either we could do it by a line, a little curvy line there, and if like the number of curvy lines is the same for all of them, that would mean that they're all equal to one another. Okay, and so we would call this one equiangular. Another way that we could do it, and I think this is how they do it in the book, is they have a single line, single curvy line, but they did the same thing we did over here for the equilateral. They took the single curvy line and they put a little tick mark there. Since all of these only have one tick mark, it means those angles are all equal to one another. Okay, so we say that's an equiangular polygon. So the measure of the angles are the same. Equiangular, right? That makes sense. Equilateral, the length of the sides are the same. So that'll maybe help you remember equilateral. And what if we have a scenario where both the length of the sides and the length of the so the length of the sides are the same and the length of the angles are the same? If that's the case, then we say this is a regular polygon. So a regular polygon is both equiangular and is equilateral. All right, both of those things are true for a regular polygon. Yeah, just the way they did it in the book, just to keep from confusing you, I'll put 2 tick marks for the length of the sides and use the 1 tick mark for the length of the angle. So does that make sense to you guys? Equilateral versus equiangular versus regular?
I have a question about it.
Yes.
So let's say, so if the angles are equal and the lines are equal, it's a regular triangle.
Uh-huh.
And if the angles aren't equal, but the lines are, then it's equilateral.
That's right. Yep. And so if they'll do the one other scenario, if the lines aren't equal but the angles are, it's equiangular. Okay. All right. Now, we said a moment ago that all of the angles in a circle, if you added up all the angles, if you drew a line to the center of the circle, all of the angles that were created by that would add up to what? Did we say in a circle? 360, right? What about a triangle? Do you guys know anything about the angles in a triangle? What they have to all add up to? Yes. It's 180. Yeah. So all angles, all angles in a triangle. There's my little symbol for a triangle. It looks like a triangle, huh? Surprising. Can't believe it. So all angles in a triangle add up to 180 degrees. All right. If we think about that, what does that mean then if we have a quadrilateral? And is it true for every quadrilateral that I could draw a dotted line between 2 opposite sides and create 2 triangles inside that quadrilateral? Do you guys agree I could always do that, right? So if every triangle has 180 degrees in it, then what do you think that the total degree of angles would be in a quadrilateral?
360.
360, yeah. So all angles in a quadrilateral, I don't have a cool shape for that, so all angles in a quadrilateral add up to 360 degrees. So that's something that you just need to know as well. Since the angles in a triangle all add up to 180, if I have a triangle like this, which is equiangular, which means what?
Means the angles are equal.
The angles are all the same. If the total number of angles is 180 and all the angles in there are the same, then what do all of these angles have to be? Yep. They have to be 60 degrees. Do you guys see that? This one has to be 60, this one has to be 60, and this one has to be 60, because that's the only number that will all add up to, that's the same and will add up to 180. Because 180 divided by 3 is 60, right? So make sure you understand that. If you know that it's a regular triangle, or if you know that it's an equiangular triangle, Or as it turns out, even if it's an equilateral triangle. Because for a triangle, if the angle is the same, then the length of the side across from the angle is also going to be the same. All right? So that it'll always have 60-degree angles in a regular triangle. Or an equiangular and an equilateral triangle. The point is, if it's a triangle, if it's equiangular, it'll also be equilateral. The opposite, the length of the side opposite the angle will be the opposite angles will be the same. If we had a regular quadrilateral, so remember what regular means. Regular means the length of all the sides is the same, and it also means that all the angles are the same. So it should make sense to us if it's equiangular and it's a quadrilateral, since they add up, so this adds up to 360. 360 divided by 4 is 90, so it should make sense to us that all of these angles are 90 degrees. And so for a quadrilateral that is equilateral and equiangular, or in other words, that's regular, we say that is a square. Right? The length of the sides are all the same, and all of the angles are 90 degrees. And then they've got a picture in the book of a regular pentagon, a regular hexagon. I would just say, you can't, if you see a picture, right? You see a picture like this, and this is all I've given you, and you look at that and you go, well, it looks like the length of the sides are all the same. You can't just automatically say that's equilateral. I would have to label that somehow. I'd have to do something like this to let you know for sure that the length of the sides are the same, okay? So don't assume just by how the picture looks. Make sure there's some sort of marking that tells you that the length of the sides are the same, or that the length of the angles are the same. Wow, there's a lot of definitions in this one. This is taking us a while to get through. What about, let's make sure we know this. So this triangle is different from this triangle, which is different from, actually, let me draw that a little differently. Draw it like this, which is different from this triangle. All right, we have different classifications for each of these triangles here. What do we call this triangle?
A right triangle.
A right triangle. Why do we call it a right triangle?
It has a 90 degree.
Yeah, 90-degree angle, which we also call a right angle, right? So that would be a right triangle. Any triangle that's got a 90-degree angle in it is a right triangle. If you have a triangle that has nothing but acute angles in it, this would be an acute triangle. And then if it's got one obtuse, in this case it's this one here, obtuse is what? It's
180.
no.
Larger.
It just
than-
means it's larger than 90, right? So any angle that's larger than 90 is obtuse. So this would be an obtuse triangle. All right, so make sure you know those classifications. An isosceles triangle. This is actually an isosceles, pretty close to it. An isosceles triangle only has two sides that are the same. So if I were to draw this triangle and I asked you to give me the most specific name, give me all the classifying names for this triangle, you would have to say this is an isosceles. I always forget how to spell that word. Yeah, there's a S there. Isosceles acute triangle. Because it's got two sides that are equal. The length of two sides are equal, and only two sides. And then all of the angles are smaller than 90 degrees, so it would be acute. Now, if I said this was the case, what would we change the name to? Yes?
Equilateral.
I would say an equilateral acute triangle. But what did we say about triangles? If the sides are all the same, what does it mean about the angles, and vice versa? This is only true in a triangle. If all of these angles here are the same, then it means that the sides, the length of the sides have to be the same in a triangle. And it's also true, the reverse of that's true. If all of the length of these sides are the same in a triangle, then the length of the angles will all be the same. So actually the best way to describe this one is that it's a regular acute triangle. Okay? So sometimes I may ask you to give me multiple names, choose the most appropriate name, but there may be multiple names that you put in there because it's both acute and in this case it's also regular, okay? The last thing that they note is you could have what's called a scalene triangle, and so a scalene triangle just means that none of the sides have the same length. So if all of the sides have different lengths, then we say it's a scalene triangle. All right, finally, we can get to some problems. And let's make sure I don't lose track of time. So we started at 9:45. So we get out 11:10.
Yeah.
All right. So let's do just a quick example. And I'm not going to do the one in the book, but you guys will have to think through this. Let's say that this is 25 degrees, and we'll make this one here. Actually, I'm going to make it bigger than that. We're going to make it 55 degrees, and we're going to say this one right here is 75 degrees. What is x in this case? How would I determine x? You know, Cohen?
Yeah. You add both of those angles and then you subtract it from 180.
Right, yeah, so like Cohen said, we remember that for a triangle, all the angles have to add up to 180 degrees. So we could add both of these together and then subtract it from 180 to get what x is. Another way to say that is I could write it like this. X is equal to 180 minus each of the other angles, right? That would be another way that we can do that. So 180 minus 75 minus 55. So when we do that, 180 minus 75 is 105. And then when I take 55 away from that, I'm going to be left with 50. So x equals 50 would actually be the answer for that. Okay? Does that make sense to everybody? This one's kind of tricky. For this one, they said that this and this, and we want to find y, we want to find x, and they tell us that this other angle here is 50 degrees. How would I figure that one out?
X would be 50 because they all have the same angles. Would that be right?
X is equal to 50, that's right. How do you know that x has to be the same as that guy?
Because I don't know how to describe it, but the lines are kind of showing how they're all the same length.
Yeah, so because this line here is the same length as this line. What kind of triangle is this because only two lines are the same? Isosceles, right? It's an isosceles triangle. And remember what I said, anytime the lines are the same length in a triangle, just in a triangle, if the lines are the same length, then whatever angle is opposite that line is going to be the same as the angle in any other lines that are the same length. So these two angles have to be the same because the lines opposite those angles are the same length. Does that make sense to everybody? I want to make sure that's clear. So that tells us right away then that x has to be 50. So if I know that x is 50, can I figure out y now? I can figure out y using the same method we used before, right? I can just say y is 180 minus 100, since 50 plus 50 is 100. So that other angle has to be 80 degrees, and so y equals 80. By the way, notice I didn't say y equals 80 degrees because it's y degrees up here. The degrees is already there for us, so we would just say the y is equal to 80. I'm not going to count it wrong if you put 80 degrees, but that's why we only put 80 there instead of putting the degree symbol in there. And we're not going to do this. Well, yeah, maybe we will. Actually, I want to make sure you guys get this. So, what if we had something like we have here, where we said this was 8, this was 8, at a length of 8. I want to find out what y is. I want to find out what x is. And we're going to say that this angle here, my angle doesn't quite look big enough to be what they put, so I'm going to say that my angle is 100 degrees. How would I figure out what x and y are? Yep.
Since they're both 8, they have to be the same angle, so then it's 40.
I can do what?
They have to be the same.
They have to be the same angle. Yep. So how would I go about figuring it out?
Subtract 100 from 180 divided by 2.
Divide by 2. Yeah, exactly. So did everybody follow her logic there? Because this is 8 and this is 8. That would be just like in our last figure, putting a tick mark there and a tick mark there. They're the same length, right? And so that means that x and y have to be equal to one another. So I could kind of rewrite this thing and say this has to be x and this has to be x. They have to be the same. And so now I'm saying, well, whatever's here, when I add those together, I have to get whatever's left when I take away the 100 from the 80. So 180 minus 100 equals 80 degrees. So these two angles added together have to equal 80 degrees, but they have to be the same. So it's really 80 divided by 2, which equals 40. They have to both be 40 degrees, right? So x equals 40. This was y before. Y has to also equal 40. And we can check ourselves to make sure we got it right and say, hey, if I do 40 plus 100 plus 40, do I get 180? And I do, right? That adds up to 180 degrees. Did that make sense to everybody? Now, if I wanted to do it algebraically, if I wanted to write a little algebra equation, this is what I would do. I would have said, okay, these have to be the same, so I'm just going to think of both of these as being x, because the x and the y have to have the same value. And this is what I know. I know that 100 plus x has, 100 plus x equals 180 degrees. And so that means when I combine like terms, 100 plus 2x equals 180. When I subtract the 100 from both sides, I get that 2x equals 80. And then I want to get the x all by itself, so I'm going to divide both sides by 2, and I'm going to say x equals 40. So I get the same answer, right? How many people, though, when I did it this way, went, what? What just happened? How many of you are good at doing this, and how many of you are like, not so much, we need to work on that? How many of you are like, I need to work on that a little bit? Yeah, all right? That's why you're here, all right? This is one of the key things that I sent out an email to parents at the beginning of the year, and it's like, your kids need to know how to do this. This is super, super, super important, right? This is just working with simple algebraic equations, being able to combine like terms. We're gonna, you should have seen this before, but we're gonna reinforce this over and over again. So I'm gonna give you plenty of opportunity to try stuff like this out. If you've already got this, great. Don't forget it, right? You're gonna need it going forward. This is one of those key concepts that's just gonna apply from this point on. If you go through college, you're gonna need it in college. Any other high school classes you take here that are like math or science related, this is probably going to come up again. So make sure that when we start learning this kind of stuff and reviewing this kind of stuff, make sure you get it down, okay? That is not the time to doze off when we're talking about stuff like that. All right, just a couple more definitions. I'm not going to write it down on the board for time's sake because we need to move on and get to these other sections. But if you'll look on page 8 at the top, does everybody have the book, by the way? Everybody got one? Okay, just want to make sure everybody is able to look on with me. They identify a parallelogram. Parallelograms have two pairs of parallel sides, so the sides opposite one another are parallel, and it turns out that opposite sides also have the same length. You could prove that's true in geometry. We'll probably walk through a proof of that. But that's a parallelogram. Opposite sides are parallel, and the sides have the same length. A trapezoid only has two pairs of opposite sides. The other two sides are not. It cannot have four pairs. I'm sorry. It can't have. It has two sides that are parallel. Not all opposite sides are parallel. Let me say it that way. So it can only have one set of parallel sides. A rectangle is like a parallelogram in that all opposite sides are parallel and opposite sides have the same length. However, the rectangle also has 90-degree angles at each corner. A rhombus basically looks like a square that's been sort of skewed sideways, so it has the same length, but it doesn't have, all the sides have the same length, but they don't have 90-degree angles there. And then if we squared it up, made it have 90-degree angles, a rhombus turns into a square, okay? So I don't know, I think they're just giving you those shapes just to remind you what those shapes look like. I don't think there are any homework problems that actually require those, so we're not going to spend much time there. Just want you to see it. You'll definitely have to know those when you take geometry, so we'll relearn those in the geometry class. And I hope all you guys will take the geometry class from me next year. That would be awesome. And we could put some of this stuff into practice that we're learning this year. All right, let's talk about perimeter and circumference. Who can tell me how I would find the perimeter of this figure right here? Of that quadrilateral. Let's say that I told you that the length of this side was 4, this was 5, we make this one 7, and we'll make this one 7 also. How would I find the perimeter of that figure?
You'd add up all the numbers to
Yeah.
your area.
You just add up all the length of the side. So if we said this was, for example, we told you that the length of the sides was inches, then the perimeter of that figure would be, we could start anywhere. We'll start at the bottom, 4, and we'll work our way around. 4 plus 5 plus 7 plus 7, right? And so that's 4 plus 5 is 9, plus 7 is 16, plus 7 is 23, and so we would say that the perimeter of that quadrilateral is 23 inches. All right. We would always, if I give you a unit of measure, you're always going to want to include that unit in there. So make sure that if I say it's inches or meters or whatever, that your answer has that value in there. But that's the way perimeter works. You just add up the length of all the sides, all the way around the polygon, and that'll give you the perimeter of that polygon. Okay. Now we can also, excuse me. So here's a really useful triangle that you're going to, I'm teaching an SAT prep class, and we had to go over this yesterday. The 3, 4, 5 triangle, which is a special triangle that you need to remember for the SAT test. What would the perimeter of the 3, 4, 5 triangle be? Simple enough, we could just do it in our heads, right? Anybody want to tell me what the perimeter would be?
The triangle?
Uh-huh.
Would be 6, right? Or would it be just 12?
It would be 12. We add them all up, right? 3 plus 5 plus 4. 3 plus 5 is 8, plus 4 is 12. So the perimeter of this guy would be 12. So it doesn't change. For any polygon, that's always what you do. You just add up the length of all the sides, okay, to get the perimeter. Now, for a circle, we also sometimes want to find the perimeter of a circle. But for a circle, we don't call it perimeter. You guys know what we call it in a circle? Cohen? What, radius? No. What does radius represent? You know what it represents. What does it represent?
It's the inside from the center to the out.
Yeah, so if we draw a line from the center point to the outside, that's what we call our radius. Let me ask Alexa.
What the outside is?
Yeah, what is it?
Circumference.
It's the circumference, right? So perimeter for a circle, what we think of as the perimeter, right, you guys do realize, like if I wanted to calculate the perimeter of my house, if I had a long enough measuring tape, I could just start at one corner of the house and stretch the measuring tape out and then walk around this way and walk around all the way. If I took that measuring tape all the way around, whatever number I got at the very end would be the perimeter of my house, right? The same thing for a circle. If I had a measuring tape, I would just start at one point and I would go all the way around, and it's the distance all the way around that circle. But for a circle, we don't call it perimeter. We call the distance around the circle the circumference. So we have a special name for it. And so this is one of those that it's a common enough it's a common enough problem. It's something that we have to find in a common enough way. I'm having a hard time to say that in English. But it's such a common problem that we have to solve that it's something that you guys need to memorize the formula for. So does anybody know what the circumference of a circle is?
2 times r times pi.
Yeah, so normally we write it like this. Normally we write it as 2 pi r. All right? We put the r last there. Where r represents the radius, as we've drawn it here. Now, what if I don't give you r? What if I instead give you the distance from one side of the circle to the other? Somebody else tell me, what do we call that? Yes?
It's just,
That's the diameter, so we would label that with D. So you know what the circumference formula would be with D? It's just what? It's not. So you're close. You're thinking the right way, but you let's think about it like this. How does R relate to D? How many R's are in D? 2. So isn't it true that D equals 2R? Right? So let's take this right here and let's just rearrange it. All those are multiplied together, so we can write them in a different order. In fact, we're going to write them in the order I think that you said it, Cohen. If we say that circumference is equal to 2R pi, isn't it true that this portion right here, 2R, is the same as D? So we could just rewrite this as D pi. But we actually typically write it, we put the pi in the front. We usually put our non-pi variable at the very end, and we would write it as pi D. All right? So that's the circumference. If you have the diameter, you can think of it that way. If you have the radius, you can think of it that way. I'll tell you, I never think pi D. I never think that. If they give me the diameter of a circle and I'm asked to find the radius, you know what I do? I take half the diameter that they give me and say, that's the radius, and then I think 2 pi r. It's just the way that I always think about it. Because I only have to remember one equation, right? I remember that the radius is half of d, and so if they say the radius of this circle is 10, if they say the diameter of this circle is 10, find the radius, I go, okay, the diameter is 10, that means the radius is 5, so 2 pi r, 2 times pi times 5 would be my radius, which is 10 pi, okay? Now in this class, when we think about pi is one of those numbers that that just never ends, right? You ever heard the song that never ends? It just goes. That's the way pi is, right? It's the number that never ends. It just goes on and on, my friend. Anybody know that song? Okay. Is it gonna be stuck in your head the rest of the day now? That was my goal. So in this class, when we do pi, it's really long and complicated number, 3.14, and it just keeps going, never repeats. But in this class, we're just going to use 3.14 for pi. All right, so you don't have to get any more complicated than that. So, if I tell you that I want you to find the radius of this circle, I want you to find the circumference of this circle, and I tell you that the diameter equals 10, then how would I calculate the circumference? Anyone? Yes?
3.14
Times 10, yes. So I can take this part of my formula right here, pi d, and I can say it's 3.14 times whatever the diameter was that they gave me. We're gonna add meters to the end of this just so we'll have a unit. So it's 10 meters. And then we're gonna punch that in our calculator, or we're gonna already be good with multiplying decimals and numbers that are powers of 10 together, and we're gonna say all I have to do actually is just move my decimal place one place to the right, and I know that my final answer is gonna be 31.4 meters. If that's not a trick that you guys already know, that's a trick that you should learn. Any decimal, right? We'll just use 3.14 as our example. If I multiplied that times times 10, then because 10 is a 1 with only one zero after it, then I'm going to move the decimal place over one place, and my answer is going to be 31.4. If I do 3.14 times 100, I have a 1 followed by 2 zeros, so I'm going to move my decimal place over 2 places, and my new number is 314. If I do 3.14, I'm going to put a 0 here because we can add zeros onto the end of any decimal and we don't change the value of the decimal. If I have 3.14 times 1,000, since I have 3 zeros, I'm going to move my decimal place over 3 places, and my answer is 3,140. So you can just kind of keep doing that, right? So that's a little trick that you need to be familiar with. The reverse happens when you divide your decimals. So if I had 31.4 divided by 10, I've got 1 0 here, so I move my decimal place 1 place to the left, and the answer is 3.14. So you can kind of go back and forth with that. That's a really handy trick. Like I said, if I thought about it the way that I did, instead of thinking about it the way that, is it Allison? The way that Allison did, I like to think of it in terms of radius, because that's the formula that I remember. So as soon as they gave me d equals 10 meters, I just said, well, that means that r equals 5 meters. And so when they asked me for the circumference, I know that that's 2 pi r. And so I know that that's 2 times 3.14 times 5. And 5 times 2 is 10, and 10 times 3.14 is also going to give me 31.14 meters. You can do it either way that you want. Totally up to you. I just like the idea of only having to remember one formula instead of remembering two. All right, let's. We had some problems like we had. We'll do one of these problems. We had a problem like this on the test. It was a little more complicated than this. Let's just make sure we can follow this. If I have a figure that looks like this, and they tell me that the length of this side is 10, and they tell me that we've got a length of 3 there, and they say that the dimensions are in inches. So inches are the units that we're going to use, and they ask us to find the perimeter of this figure. Remember what perimeter is. If I took a measuring tape at this corner right here, and I could go all the way around this, all the way back to there, I'm just trying to find that length, right? That's what perimeter represents. The distance all the way around, the length all the way around that figure. And so I've got to realize that this figure here is actually 2 shapes put together, right? What are the 2 shapes that I'm thinking of?
A half circle and a rectangle.
A half circle and a rectangle, exactly. And so that's going to help me do the perimeter. I got to know the length of these other sides, though. So what is the length of this top side here? That's an easy one.
10.
That's also 10, because we've got a rectangle here. What about the length of this side?
It'd be 6.
Why?
Because the radius is 3, and then it's like half of the circle, and then you just times it by 2.
Yeah, so I could if this is 3 here, this is the center of my circle, then that also means that this distance right here is 3, and this distance right here is also 3. Does everybody see that? And so that means that the total length of this side has got to be the 3 and the 3 added together, which is 6. Okay? So that'll give me part of my perimeter. I can say 10 plus 6 plus 10, but then I have to also add to it this distance right here. How do I figure out that distance? Well, you guys have already said that's half the circle.
Yeah. You
Right?
do circumference and divide it by 2.
So I take the circumference and divide it by 2. So let's figure that up first, right? Circumference of a circle is 2 pi r. And I'm going to take that circumference and I'm going to divide it by 2, because I've only got half of a circle, right? Look at what happens as soon as I do that. My 2's cancel out. So the half circumference that I'm looking for is actually going to just be pi r, right? So pi times 3, I could write that as 3 pi. And if I want to get a decimal answer for it, now I don't know if that's what they did in the book. I'm guessing they did. Yeah, 9.42. Right, 9.42 inches would be that length. So this is 9.42. So now that I've found all of the lengths there, finding the perimeter is going to be super simple. I just add them all up. It equals 10 plus 6 plus 10, and then plus this distance right here, which we found to be 9.42. So when we punch all of that in our calculator, we get a value of 35.42, and then like I said, don't forget that our distance was in inches, so put your unit on the end of that. Okay? Any questions on how I did that problem? You guys think you could do it on your own? All right? I like it. Excellent. All right, let's move on to the next section. We're just going to do these 3 sections today. This section is really long, but I'm not going to go through all of these sections because all of these all of the things that's in here because it's talking about a review of arithmetic. You guys have been doing arithmetic for a while, right? So hopefully I don't need to spend a lot of time on this. There are a couple of key points that I want to make sure that you understand. And so this is lesson 4. One thing that I want to make sure that you guys know, well, first let me say this. You should read through this chapter. Just read through it and make sure that you understand everything. They give you some definitions like counting numbers. Counting numbers are, another name for that are natural numbers. So it's like where we start counting, right? 1, 2, 3, 4. It's just all of those numbers. Starting with the number 1. Those would be our counting numbers. When we talk about real numbers, a real number would be any number, including 0, which is either positive or negative. So anything that we could sort of identify on a number line as we go up and down a number line. So a decimal number or a fraction number, whether it has a positive sign or a negative sign in front of it, those would all be considered real numbers. They talk about number lines on here, and again, I'm assuming that you guys have seen number lines plenty of times before, and so you shouldn't really have any problem understanding the concept with number lines. This is something I want to make sure that you get, because some people are still kind of fuzzy on this. So if we have a fraction like this, 4/3 times 15/8. How am I going to do that problem? How do I multiply two fractions together? Yep.
You're going to make the denominators equal.
Do I need to do that, guys?
Actually, no. This is
Why don't I need to?
Because we are not adding or subtracting.
That's
we're
right.
just multiplying.
We're multiplying. So when we multiply, we don't have to worry about that. We can just multiply the numerators together and we multiply the denominators together. But there's a step that I want to make sure you know that you can do first to simplify that process. And Kirsten's going to tell us. What is it, Kirsten? Are you?
Not Kirsten.
Oh, you're not Kirsten. Sorry. You are Allison. I knew that. Allison's going to tell us. Yes.
Cross reduce.
I can cross reduce. Which one's Kirsten? You're Kirsten, right? Okay. So cross reduce. So what she means by that is I recognize that both this number, if I've got a number on top of the fraction on one side, in one fraction, and on the bottom of the fraction of the other fraction, then if they're divisible by a common number, then I can divide both of those by that. So this is divisible by 4, which gives me a 1, and this is divisible by 4, which gives me a 2. So I'm going to reduce in that fashion, right? These are both divisible by 3. So I'm dividing that by 3 to get 1. I'm dividing this by 3 to get 5, right? So now I have 1/1 times 5/2. This becomes super simple at this point, right? So my answer is 5/2. So that cross reducing is really going to make that simpler for you. Now, if I had multiplied this together, if I had said 4/3 times 15/8, that would have given me 60/24. Whoops, not 25. 60/24. And if I reduce this down, I would get 5/2. But that's a lot more complicated, right? The math's a lot harder, and sometimes these numbers here could be huge when you could have just done the reducing up here and made your life a lot simpler. All right? What if instead of 4/3 times 15/8, what if I had 4/3 divided by 15/8? How am I going to do that?
The way I learned it was keep, change, flip. You keep the first one and then change it to multiplication and then flip the
Okay, keep, change, flip. I like it. I haven't heard it described that way, but that's exactly what we're doing, right? So we keep the first one, like Will said. We're going to change from division to multiplication, and then we're going to flip this fraction. What's it called when we flip that fraction? What is this fraction compared to this fraction? Does anybody know the term? Yes.
Invert multiply?
No, that's not the term I was thinking of. You are inverting and multiplying. So that's your term for the keep, change, flip that Will just said. But what is, if I have 15/8, what is 8/15 compared to 15/8? You guys know the name of that?
improper.
No, this right here is the reciprocal. You guys ever heard that? The reciprocal. So if I tell you to take the reciprocal of a fraction, we mean flip that fraction. All right? So when you divide by a fraction, you're actually you're going to instead multiply by the reciprocal of that second fraction. Okay? And so at this point, can we cross-reduce? We can't. Now that we could up here when we were multiplying together, but now that we flipped them, because the 4 and the 8 are both in the numerator, we can't cross-reduce. So we're going to have to just go ahead and multiply through and say that 4 times 8 is 32 and 3 times 15 is 45. And then we could look at that and see if we could reduce that any further. I don't think we can we? You guys see any way to reduce that?
No.
I don't. All right, so that would be our answer for that. All right. One other thing, like I said, read through all of these and make sure that you understand the terminology. Something that's going to be really, 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 really important, especially when you get in my chemistry class, is you guys have to know how to use unit multipliers. All right, so I want to make sure that we don't miss this. If I'm saying, when we said we needed a common denominator on one of the problems a minute ago, let's just say we have something like 3/7 plus 4/3. And we say we want to get a common denominator, and in this case we want to make the common denominator 21. All right, so we said what we're going to do is we're going to take 3/7 and turn it into something that's over 21. But in order to do that, we're going to have to multiply the top and the bottom by 3, right? And why did we say we had to multiply the top and the bottom by 3? Whatever you do with the bottom, you do with the top. And the reason this doesn't change the value is because we said 3 over 3 is 1, right? So we're just multiplying this number times 1, which isn't going to change the value of the number. That's exactly the way that unit multipliers work, okay? What do I mean by unit multipliers? Well, everybody knows that 12 inches equals 1 foot, right? So that's what we call a unit multiplier. So since these are equal to one another, just like 3 is equal to 3, if I put 12 inches over 1 foot, what's the actual value of that? What's the numerical value of that? If I have two numbers that are equal to one another and I put one over the other,
Just 1.
it's just 1, right? This right here just equals 1 because those are equal to one another. Do you guys see that? It's just like 3 over 3. And so that's why with unit multipliers, we can convert from one unit to the other by multiplying by that unit multiplier. So for example, if I told you that you have 3 feet, and I want you to tell me how many inches that is, you can say, well, I'm going to multiply 3 feet. I think of 3 feet as being 3 feet over 1. Right? Any number can be a fraction by just putting it over 1. I'm going to take that and I'm going to multiply that times my unit multiplier. And my unit multiplier is this. Now, because these are equal, I could either write it that way or I could write it this way. Right? Both of those will equal 1. It's two things that are equal over one another. Right? And so if I want to convert this to inches, which one am I going to pick? Am I going to multiply it times this, or am I going to multiply it times that? First one or the second? Huh? You say the second? I want to end up with inches as my unit, and that means I want my feet to cancel out. So the first one, right, actually would make it possible for us to do that. Do you guys see that? If I write it like this, I have feet on the bottom here, on the top here and feet on the bottom here, and they cancel out, and I'm left with inches up here in my denominator. In my numerator. 3 times 12 is 36, and the unit is inches. So that's how I would use the unit multiplier. Now I would use the second one. I would choose the second one, Cohen, if I'm going the other direction. So if I said I have 2.5 inches, and I want to convert that to feet, then I would multiply that times 1 foot over 12 inches. Now, this is on top of the fraction here. Inches cancel out, and I'm left with feet on top. So whatever 2.5, my answer would be 2.5 divided by 12 feet. And I don't know, we'd have to punch that in the calculator to see what that was. Let's just so you'll see it. 12 divided by, 2.5 divided by 12 equals, we're around that at 0.21. So the answer would be 0.21 feet, okay? It's super, I want you guys, when you do these unit multipliers, I want to make sure you understand that. They're going to give you an opportunity to kind of chain them together, all right? Put multiple unit multipliers together. And we do that all day in chemistry. Like if you can understand unit multipliers, you can ace chemistry. All right, if you can get this concept down right here. So this is super, super important in chemistry and in other disciplines. So make sure that you understand the unit multiplier portion as you're going through that. What I want you to do today for homework next week is, and I'll post this in ThinkWave, but I want you to do lesson 2 through 4, all right? All practice and all odd numbered, or whatever the other section's called. What is it called? Problem set. All odd numbered problem set. All right, so that'll be your assignment for this week for lessons 2 through 4. All right? And remember, study the material and prepare for a short quiz. It'll be a quickie, a quick, probably multiple choice quiz at the beginning of class next week. Any questions for me? All right, you guys have a good one.